Hi, I want to shoot a little addendum, a little third part, in which I compare and contrast what we mean by a state of a particle or state of an entity in classical physics versus quantum mechanics. Okay, let me try. Okay, so this is classical, and this is quantum. And this is, right. So in classical physics, at any given time in classical physics, the state of a classical particle is given by its position and momentum, or loosely speaking, velocity. I was a little imprecise before when I said that it's given by position. What I was trying to say is that as time evolves, you get a bunch of positions, and so what results is a set of values of position versus time, which is a trajectory. But at any given moment in time, the state of a classical particle is given by position and momentum. It could be in 2 dimensions, 3 dimensions. Usually we use the letter P. So basically, position and velocity, right? And if we know position and velocity, if we know velocity, we know position at the next instant of time. And if we know the position, we know what forces are acting on the particle, and so we know how the velocities will change. So therefore, if we know position and momentum, we'll be able to compute position and momentum at the next instant of time, the next instant of time, and so on. In quantum mechanics, at any moment of time or any instant, even this is not really a precise language. Particle is particle. It follows the laws of nature. A more precise statement would be a classical description of a particle versus quantum description of a particle. It's not really right to say that particle is classical or quantum. Particle is, it is what it is, but we can describe it using different laws. In some cases, classical description is good, and in some cases it's not. So it's not really right to say classical particle versus quantum particle. Is given by a wave function which is a function of space, right? So it's a wave function of R. So that's a way I can expand that for you. It's a wave function of X, Y, and Z. And I'm suppressing time because I'm saying at any given moment of time. Now is a statement about evolution. Okay. The evolution of R with time and momentum is given by classical equations of motion. The one that you're familiar with is called Newton's equations, but it's not the only one. There are other ways to describe dynamics of classical particles that is more powerful. So this gives position as a function of time. So again, if you know momentum, you know how position will change. You evolve position over time delta t, and then you can recalculate the new forces. And so if you know the new forces, you know the new, you can calculate the new accelerations, which tell how the momentum will change. So you update the momentum and so on. So it's like a clockwork. On the other hand, the evolution, so this is the state, and this is the evolution of the state. This is the state, and this is the evolution of the state. Evolution of psi with time is given by something called the Schrodinger's equation. I will not put the dots in the future. It's kind of hard. And so this gives, so this gives the position with time. This is trajectory. And also momentum with time. And this gives evolution of the wave function with time. So at T1, the wave function could be like this. At T2, the wave function could be like this. At T3 could be something like this. So the wave function evolves, right? So this is, for example, space, and this is the wave function. And the wave function, being the function of space, evolves in time. Okay? So the evolution of the position and momentum gives rise to the trajectory, also gives us the history of the momentum, and that's it. But what is wave function good for? It's kind of an esoteric thing. And the wave function is good for calculating probabilities. This part doesn't exist in classical mechanics. Or not at, but I should say around. And that's not the only thing that the wave function gives. So psi also contains other information, other statistical information. Okay. And you can begin to see how the wave function description of a particle, the stochastic or statistical description, is incompatible with the notion of a trajectory. These two things, point 3 right here and point 2 right here, they're really incompatible, because if you have a probability, that means if you measure the particle, you can find it here. When you release it, next time you can find it here. When you release it, then you can find it here. And so in general, you will get some kind of a disorderly set of places where a particle is found. Whereas the classical description of particle is a smooth trajectory. Moreover, you can do an experiment, you can do an ensemble of experiments. All right, let's say in all of those experiments, you caught a particle here, right? You sift out and you select all the experiments where you caught the particle here. Then in each of those experiments, when you catch the particle a moment delta t later, in some you will find the particle here, in some you will find the particle here, in some you will find the particle here. But this randomness aspect is not present in the trajectory description. So you can begin to see that the trajectory description of particle, of evolution of the state of the particle in classical physics is really quite incompatible with the evolution of probabilistic description in quantum picture.